class. Here is your physics video for Wednesday, February 24th. Today, we're going to explore a little deeper what happens with kinetic energy in collisions. We briefly talked about this earlier when we talked about elastic collisions versus inelastic collisions. And I want to go into a little bit more detail today. And we're going to use this table for some illustrative purposes. So the first thing I want to talk about here at the top, perfectly inelastic. What do we mean here, perfectly inelastic? In a perfectly inelastic collision, two things are going to hit each other and they're going to stick together. So think of maybe if somebody throws a chunk of clay and you hit it with a baseball bat, right? That clay kind of sticks to your bat. It doesn't go bouncing off like a baseball would. Or think of maybe a skateboard on the ground and it's sitting still and you run and then you jump on the skateboard and then the skateboard and you move off together. So I mean by the objects sticking together, they have the same final velocity. In a perfectly inelastic collision, we know that momentum is conserved. Momentum is conserved, key point, but our kinetic energy is not conserved. Very, very, very important here. Some of our kinetic energy is transformed into a different form of energy, heat or friction or deformation of an object. Some sort of internal energy is going on there. The energy is being conserved, but not simply kinetic energy. We can also then talk about a perfectly elastic collision. Think of an elastic collision. These are where things bounce off of each other. In fact, they bounce off each other very efficiently so that our kinetic energy is conserved. Some examples of this might be like think of billiard balls, pool balls, right? You're on the pool table, you hit them, they bounce off each other really well. Maybe think of a super ball or a bouncy ball. You drop it on the floor, it hits that floor, it bounces off really high. We don't lose a lot of the kinetic energy. Right? Think of that extreme there where the kinetic energy is conserved. We call that elastic collisions. And then we have some place in between where they're still inelastic, but they're bouncing off each other. So they're going to have different velocities as opposed to our perfectly inelastic at the top that has the same velocity. Now let's finish off the rest of our table here. Momentum is always conserved. Doesn't matter what kind of collision we have, momentum is always conserved. But from kinetic energy perspective, it is only conserved in a perfectly elastic collision. If there's any elasticity at all, any inelasticity at all, the energy is not conserved. So let's go ahead and put this into use into some problems. Let's talk about this. Two toy trucks with clay on their front bumpers collide head-on in a perfectly inelastic collision. There's that clay there. It's going to stick together. That's what we mean by perfectly inelastic. The first truck has a mass of 0.5 kilogram and an initial velocity of 4 meters a second to the right. The second truck has a mass of 0.25 kilogram and an initial velocity of 3 meters a second to the left. So just to make sure we're clear here, perfectly inelastic, right? That means kinetic energy is not conserved here. Kinetic energy is not conserved here. So we can't use that to help us solve the problem. All we can use is conservation of momentum. So let's make a picture of our scenario here. We've got two trucks. So here's truck one, here's truck two. Truck one is 0.5 kilogram. Truck two is 0.25 kilogram. And truck one is moving to the right at 4 meters a second. Truck two is moving to the left at 3 meters a second. I highly advise drawing pictures like this. It'll really help you as you're doing your calculations. So let's figure out what is our initial momentum. Remember how we calculate initial momentum? Momentum is just mass times velocity. We have two objects, so we calculate the momentum for each object and then add them together. Let's go ahead and plug in the numbers that were given to us in our problem, that 0.5 kilogram for the truck one times 4 meters per second, and then the 0.25 kilogram for truck two and the 3 meters per second for its velocity. I want you to note here, though, look at how we did our math here. That velocity here for the second truck is negative. It's moving in the negative direction. Be very careful. Momentum is a vector quantity. Direction is important. So make sure you remember that. Again, the direction of the momentum is the same as the direction of the velocity. So we go ahead and we finish our calculation and we figure out that our initial momentum here is 1.25 kilogram meters per second squared. Now this is important because In our problem, it doesn't tell us which direction the trucks are moving after the collision. All it tells us is that they're stuck together. By looking at our final answer here, we see our momentum is positive. So we know at the end, if our final in our final momentum calculation, we know it's got to be positive too. And the only way that can be positive is if the trucks are both moving to the right after the collision, right? Because they're both moving at the same velocity. So then we know when we draw our picture here of our after condition, which put our two trucks are stuck together. Right? The first truck is a 0.5 kilogram, second truck 1/4 kilogram. They're stuck together, so they're moving at the same velocity. And we're going to draw that velocity to the right because we saw when we solved for our momentum on the left, our initial, we had a positive net momentum. We have to have them moving to the right at the end and the final state, so we also have a positive net momentum. So let's go ahead and calculate that net momentum. Right? Here, because they're stuck together, we can simply add their masses together, that 0.5 and that 2.5, and then we're going to multiply by the velocity. Now, we don't know our velocity yet, so we're just going to leave it as a variable, 0.75 kilograms times v. Now, we know that the conservation of momentum tells us that pi, p initial, has to equal pf. And now let's plug them in. Let's set these two equations equal to each other. 1.25 kilogram meters per second for our initial momentum, 0.75 kilograms times v for our final momentum. And let's go ahead and divide those sides. And we're going to see that our v is 5/3 meters per second. Now, I left this in a fraction because we're going to be doing a calculation next. And if we do some rounding, we're going to get rounding errors. And so I've tried to leave it as precise as possible here. Our next question asks us, what's the decrease in the kinetic energy during the collision? Well, first we have to find out what the energy is before and the energy is after. Right? So let's take a look at this energy before. We have two objects. We're going to add their energies together. Now, since both of our objects, neither one of them is going up or down, we're not changing their gravitational potential energy. So we can focus simply on their kinetic energy. And we know the equation for kinetic energy is 1/2 mv squared. So let's go ahead and let's plug in the values we have because we know both masses and both velocities at the beginning. And we plug that into our equation and we see that we have 5.125 joules to get us started in our initial state. Let's do the same calculations for our final energy. Here I put E12 because they're implying they're stuck together, right? So we're talking about the two objects together. And we figure this out by, again, 1/2 mv squared. But here, right, we're adding our masses together. And again, since they're traveling at the same velocity, it allows us to do that. We know all those numbers too, so let's go ahead and plug them in. Mass 1/2 kilogram, mass 2 1/4 kilogram. We know our velocity up above was 5/3 meters per second squared. So we go ahead and punch that into our calculator, and it's going to come back with 1.04 joules. So if we want to understand the decrease in kinetic energy, what do we need to do? We need to subtract our final energy from our initial energy, and we see that we had a decrease of 4.085 joules. Wow. Almost 80% of our, just about 80% of our energy of our kinetic energy was transferred into something else, right? Probably heat and deformation here of our clay. Let's take a next problem here. This one's a little bit more complicated. Here we have two rubber balls and they're perfectly elastic collision, right? So we know that our kinetic energy will be conserved. The first ball has a mass of 1 kilogram, initial velocity of 3 meters to the right, 3 meters per second to the right. Second ball, 2 kilograms, initial velocity of 1 meter per second to the left. After the collision, the first ball has a velocity of, well, the problem initially said 2.3 meters per second. That's rounded, and it caused problems here later on. So I went through and used the exact amount here and just took it as 7/3, right? So that's 2.3333. It just matters where you drop off that decimal point. If we leave it as a fraction, it saves us some rounding errors at the end. So we're going to find out, we had to do our before picture and our after picture. So let's go ahead and put those in here. We have our 1 kilogram ball, and it's moving to the right, and it's got an initial velocity of 3 meters per second. We also have our 2 kilogram ball moving to the left at 1 meter per second. So let's go ahead and calculate our momentum here. Just like the last problem, we calculate the momentum of each object, and then we add those momentums together. Also, like the last problem, I want you to remember here, the momentum to a direction to the right is positive, a direction to the left is negative. So we have a negative velocity here for our second ball. And that's important, right? Because that's going to mean it's going to see, we're going to subtract these two instead of adding them. And we end up with a final momentum, or a total momentum of our initial state of 1 kilogram meter per second. Let's go ahead and look at it in our final state. We know we got our 1 kilogram ball, and the problem tells us that it's moving, I didn't change my label here, moving at 7/3 meters of a second to the left. Now, we can tell by looking at our first equation for our initial that our second ball has to be moving to the right. Why do we know that it has to be moving to the right? Because our momentum here in our initial state was positive. On our final state, if our ball on the left is moving to the left, the only way we can get a positive total momentum is for the ball on the right to be moving to the right. So I'm just going to draw the arrow in. Let's make sure we have it going in the right direction. We could draw it the other way. It just might mean that when you get to the end, you have to be careful on how you're interpreting your signs as you go through. You just might get a negative sign, meaning it's going the opposite direction that you expected. Okay, so let's go through. Let's do the calculation over here. What's our final momentum? Same formula we did on the initial side. Find the momentum of each object, add them together. Here again, we don't know the velocity for our second ball, so we're just going to leave it as the variable v. I also plugged in for our first ball here. It's moving to the left, so it's got a negative velocity, and I used the fully complete value 7/3 as opposed to the rounded value of 2.3. And you'll see why when we get to the next step. Next question. All right. So now that we've got these, we can set these two equal to each other. Right? We know that pi is equal to pf. Always, 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 our initial momentum is equal to our final momentum. So we go through, we set the two equations equal to each other. Let's add that 7/3 to both sides to get rid of so we can get the v over by itself. And we find out that our final velocity of our ball is 5/3 meters per second. So we can plug in that 5/3. It's positive, and we show that, yes, our arrow's telling us it went to the right. We have a positive number here going to the right. Awesome. Now, the next part of the problem says, show that kinetic energy was conserved in this collision. How do we do that? Well, we just got to calculate the kinetic energies. We have everything we need to do that. Energy, initial energy, we just add the energy of ball 1 plus the energy of ball 2. Again, neither one's going up or down, so we're not changing gravitational potential energy. So all we have to worry about here is our kinetic energy. So we take 1/2 m1 v1 squared plus 1/2 m2 v2 squared, right? And we plug in our numbers, and we come up with a final energy of total energy for our initial state of 5.5 joules. Awesome. Easy peasy, just plug in the numbers. Let's do the same thing in our final state. Final state also, we have two objects moving, so we're going to calculate the energy for each one. Again, they're not going up or down. We're not changing their gravitational potential. So we just use our kinetic energy of each, 1/2 mv squared, to calculate our kinetic energies. Go ahead and plug in our numbers. Right? And we do the final calculation. Again, here we see that our final energy is also 5.5 joules. So that tells us that our collision here was indeed elastic because our energies did not change. Okay. Those are just some quick examples of how we do energy and momentum conservation to help us solve problems. We could have done this problem up above without even knowing what our final momentum, our final velocity was for our first ball. We just had to it just made our math a little bit more complicated, but we could have done it. We could have figured out what the velocity was, both the velocity of the second ball and the velocity of the first ball, using this approach of conservation of momentum and conservation of mass. Well, hopefully that's a little bit helpful. We're going to continue on with this topic a little bit tomorrow. Thanks a lot, guys. Have a good one. Bye.